Hi, Algebra 2 honor students. This is going to be the start of Unit 8 for us. Unit 8 is going to be an extension of Unit 7. We were mainly focused on talking about quadratic equations. And now we're going to start analyzing properties among what we call hops in our course. Hops are higher order polynomials. So we're going to start exploring patterns within x to the third equations, which are called cubic equations, x to the fourth, and even higher beyond that. So to get started today, a big part of our process is going to be finding roots of these higher order polynomials. We know how to do it for quadratics, but how would I do it for cubics and beyond? Well, it's going to have to involve some division processes. So to get started, the first question is x plus 2 a factor of x squared plus 5x plus 6? And if I take the expression x squared plus 5x plus 6, and I think about the factorization, what multiplies to 6 and adds to 5 in the middle, we would get x plus 2 times x plus 3. So to answer the question, is x plus 2 a factor of this quadratic? The answer is yes. It is one of the factors of x squared plus 5x plus 6. So what we can do is we can actually rewrite this then as if I were to take x squared plus 5x plus 6 and divide it by x plus 2, the quotient, what you're left with is the other factor there, x plus 3. And because it is one of the factors, when I get that quotient, I know that there would be no remainder left over. Because we know that when we do some division, sometimes if the factor does not divide any evenly that we're testing, then there might be some sort of remainder left over. But in this case, x plus 2 is one of the factors. So let's actually backtrack for a second to something that we would have learned in elementary school, like is 40 a factor of 5,120? So if 40 is a factor, that would mean that it would divide in evenly. And oops, I must have forgotten my calculator. Oh no. So guess what I'm going to do? I'm going to do some good old long division. You remember how to do this? So you're going to say, all right, well, how many times does 40 go into this number? Well, let's start with the 51 piece of it, right? So 40 would go into 51 once. And then 1 times 40, we multiply there. You're going to subtract 51 minus 40 to get 11. Do you remember the next part of the division algorithm is bring down the 2 and then repeat the process? How many times does 40 go into 112? Well, 40 times 2 would be 80. 40 times 3 would be 120, which is already too much. So it only goes in evenly twice. 40 times 2, we said, is 80. Subtract 112 minus 80, that's going to be 32. And then we've got one more number to bring down the 0. 40 goes into 320. I think it's going to go evenly, right? 4 goes into 32 8 times. So 40 would go into 320 8 times. Okay, so therefore 8 times 40 is 320, and we can see that in the end, this last number, of course, would be the remainder from doing the division. So is 40 a factor of 5,120? The answer is yes, it is. You can actually express 5,120 by saying that it is 40 times 128. So when there's no remainder left over, we know that this is a factor. It does divide in evenly to that value. So I guess the question becomes, can we do this for polynomials? So can we do this for the example that I wrote up above, which is x squared plus 5x plus 6 divided by x plus 2? And the answer is, well, I better hope we can, because that's the only way we're going to find roots of eventually some higher order, some larger degree polynomials. So let me show you what this process looks like if you've never seen long division of polynomials before. So I'm going to take the x plus 2, and I'm going to divide it into x squared plus 5x plus 6. And just like up here, I said, well, how many times does 40 go into 51? I'm going to do something similar with our polynomials, and I'm going to say, how many times does x go into x squared? So in other words, if I take x squared and I divide it by x, that's going to give me just x here. And then what do I do to continue on with our long division algorithm? Take x, multiply it by x plus 2 to get x squared plus 2x. subtract from what you have above, which means the x squareds cancel. Just be careful here because you have to distribute that negative to here as well. 5 minus 2 is going to become a 3x. Bring down the plus 6 and then kind of repeat the process. X divides into 3x, or 3x divided by x, if you want to think of it that way, would be a positive 3. That's looking promising. What was our quotient up here? X plus 3, right? All right, so then take the 3, multiply it by the binomial x plus 2. That's 3x plus 6. And when I subtract, 3x minus 3x is 0. 6 minus 6 is 0. So we get that same remainder of 0 again. So it takes maybe a little bit longer to get used to the process with polynomials. Maybe you feel a little bit more comfortable with the process with numbers involved. But we'll get a little bit more practice in right now with how do we divide polynomials and then making a conclusion in the end about whether or not the given factor is in fact a root. So moving on to the next example, I want to now know, is x minus 1 a factor of x cubed minus 7x plus 6? So this will be number 3. And notice how I snuck something in on you here. Maybe you noticed that as I said it or as you wrote it down, but this is not a quadratic. It's an x to the third equation. It's a cubic polynomial. So when you go to set up your long division, we're going to divide x minus 1 into this polynomial. Something that's important to include is when you have a missing term, like the x squared term is missing, when you would write this in standard form, right? Typically it would have gone x cubed, x squared, x, and then the constant. You need to put 0x squared there for kind of a placeholder. It's going to make your life a little bit easier. Okay, minus 7x plus 6. Now that I have my placeholder of 0x squared in there to start the process, you're going to take the first term of x cubed and divide by x on the outside. Well, x cubed divided by x is x squared. Next part of the process, multiply through by x minus 1 to get x cubed minus x squared. And then we have to subtract. Well, x cubed minus x cubed goes away. Over here, you're going to have to subtract a negative. So when I subtract a negative, you can think of that as being a positive x squared here. So 0 plus x squared is just, well, x squared. Bring down the next term, minus 7x, and continue. X squared divided by x is a plus x right here. Okay, take the x, multiply by x minus 1 to get x squared minus x, and subtract. Well, x squared minus x squared goes away. Negative 7 minus negative 1x really becomes plus x there, right? So it's going to be a negative 6x. Bring down the plus 6. One more step here. Negative 6x divided by x is minus 6 at the end. So take that negative 6, distribute it back through to get negative 6x plus 6. Subtract that from above, and since those binomials match identically, yeah, the remainder will be 0. So is x minus 1 a factor of this polynomial? The answer is sure is. The quotient that we're left over with is the quadratic x squared plus x minus 6. So what you can notice, and by the way, sometimes that's written as the function q of x, the quotient function. So the quotient is x squared plus x minus 6. And sometimes you'll see a fancy function written for r of x, which would be the remainder, and the remainder is 0. There was no remainder here. Okay. So when you divide a linear term right here, right, x to the first would be something that's linear into something that's cubic, the quotient that you're left with will always be quadratic. And if I asked you what are the other linear factors of this cubic polynomial right here, we can actually determine that pretty easily. We know that one linear factor is x minus 1, that divides in evenly to the cubic. Well, if I take the remaining quadratic, x squared plus x minus 6, I can hopefully break that down into 2 linear factors such that I can express this cubic polynomial in terms of 3 linear factors that would multiply to give you that cubic. So this would be what? If I factor it x plus 3 and then x minus 2. So the conclusion in the end, therefore, x cubed minus 7x plus 6, the original polynomial we started with, can be thought of and written as the original factor that I divided in, x minus 1, times x plus 3 times x minus 2. So we know how to write quadratics in factored form, but this division process will even allow us to, once I divide a linear term in, get the other two linear factors that make up this entire cubic polynomial. And if I asked you for the roots right now, I bet you'd be able to tell me it real fast. The roots are 1, -3, and 2, which is going to, of course, eventually help us to make a complete graph. Okay, so I want you to try one on your own and determine if, when you do the division, 3x cubed plus 2x squared plus 6, I want you to divide that by x minus 1 and determine, is x minus 1 a factor of this polynomial? Now remember, when you set up the long division for this one, I'm just going to give you a little bit of a hint that we are missing a term again. I'm missing the x term here. So you're going to do 3x cubed plus 2x squared. You need a 0x as a placeholder there, and then plus 6 at the end. Go ahead and try this. I would hit pause at this point because I'm, in about 2 seconds, going to show you the answers. And then hopefully you can confirm whether or not you got the same results as what I have here. Okay. So if you are now done hitting pause and you're back with me, here is the example I asked you to try. We had that 0 as a placeholder there. If you do the entire long division process, in the end, I got that the remainder was 11. So if you made a mistake in the process, check the work kind of going down on the diagonal here. Make sure that you have all the same results and values that I have. But the quotient is 3x squared plus 5x plus 5. So that's the quadratic that you're left with when you divide x minus 1, but it didn't divide in evenly because of that remainder that's non-zero. So the conclusion is that x minus 1 is not a factor of this polynomial p of x. If you get 0, of course, that means it is a factor. In this case, we know that it's not. So a way that you can rewrite the polynomial 3x cubed plus 2x squared plus 6, you can write it as the following. If this is the original p of x polynomial, you can write it as the quotient q of x, what you got from dividing it in, plus the remainder. And if you remember, when you write a remainder, it's 11 over what you're dividing in, which is the x minus 1. Okay. So any polynomial could be written when you do division as a quotient plus the remainder. If the remainder is 0, that's really nice. Okay, but in this instance, this right here, this quotient plus this remainder, if I were to combine that back together again, it would get me back to this polynomial. Okay. So if we're okay with that, let's go ahead and make your life a little bit easier, okay? Because that's what we all want in today's world, isn't it? We want to make our lives easier. So here we go. There is an easier way, and our easier way is called synthetic division. Okay, so here's going to be an example that we're going to approach from a synthetic division approach instead of a polynomial division. So is x minus 5 a factor of x cubed minus 3x squared minus 13x plus 15? Now, I have nothing against polynomial division at all, but once you see synthetic division, you may never turn back until you have to do the homework with a little bit of long division. So you're going to have to do it a little bit. Sorry, Mr. Murphy's visiting us for a quick second.
Hello, everybody.
Oh, he says hello. So here we go. If x minus 5 is in fact a factor, if this is true that x minus 5 is a factor, x minus 5 as a factor means that x equals positive 5 is a root. So the reason why I need to know that is when I use synthetic division, you're testing actually this value, which is a root of the polynomial. So I'm going to put the 5 right here. in this little box. And what I'm going to do is rather than copy this whole polynomial down, I'm just going to grab the coefficients from that polynomial, which are 1, -3, -13, and 15. Okay, so first thing you're going to do is bring down the 1. And there's going to be some steps that feel sort of like long division, but it's going to look pretty different because they're not writing any x's really at all in the end. All right, when I bring down the 1, the next thing that I do is I multiply by the root that I'm testing. So I'm going to multiply by 5, and that's 5. Put that on the next line. And then you're always going to add it to the coefficient above. So 5 plus -3 is 2. And then you repeat the process. 2 times 5 is 10. Add it to the -13 above, and you get -3. Last step, -3 times 5 is -15. Add it to the 15 above, and you get 0. And you're really going to like when you get 0 at the end, because guess what that last number represents in synthetic division? This is the remainder. And we like 0 remainders because what that means is that x minus 5 is in fact a factor of that cubic polynomial. Now, the interesting thing is remember before when we had those other linear factors that we were able to find, right? Didn't we have this quadratic and we said, hey, we can factor that and break it down? Guess what these numbers right here represent? This is the coefficient of x squared in the quotient. This is the coefficient of x in the quotient. And then this is the constant at the end. These are going to be the coefficients for q of x. So I know that x cubed minus 3x squared minus 13x plus 15 divided by x minus 5 is the quadratic x squared plus 2x minus 3. And if I asked you for the other linear factors, we could certainly go ahead and factor that and break that down a little bit further. But the great thing about synthetic division is you get a quotient left over. That's that same quadratic we would get from long division. So I hope that you'll find with a little bit more practice, synthetic division will be an easier way. It's good to know both techniques. I'll eventually explain why you may need long division at certain points in your mathematical lives. But synthetic division will be pretty much a go-to for a lot of this unit. Let's do one more. Is x plus 4 a factor of x cubed plus x squared minus 10x plus 8? So remember that when we go to set up synthetic division, if x plus 4 is a factor, that implies that x equals -4 is a root. And you don't have to formally write that statement out for me every single time, but just to get ourselves started, -4 therefore is the number that goes in your box as kind of the root that we're testing within synthetic division. What I did in the example above is I grabbed the coefficients from that cubic, so 1, 1, -10, and 8. Bring down the 1. 1 times -4 is -4, plus 1 is -3. -3 times -4, oops, sorry, I'm going a little fast. I forget we're kind of new to this. All right, add it to the one above, you get -3. -3 times -4 is 12. Add it to the -10 above to get 2. 2 times -4 is -8, plus 8 is 0. Do you have to draw a smiley face? The answer is yes, you do have to draw a smiley face, and yes, x plus 4 is a factor. Okay, it divides in evenly. Now, just like we saw in the example above, if I take this quadratic x squared minus 3x plus 2, okay, these coefficients represent this quadratic polynomial. It's nicely factorable, isn't it? It's x minus 2 times x minus 1. Those multiply to 2 and add to -3. So when all said and done, the factored form of this cubic is x plus 4. That was one of the factors that divided in, times x minus 2 times x minus 1. And if I get a little sneaky here on you and I set that equal to 0, we would get the 3 x-intercepts, the 3 roots. X equals -4, x equals 2, and x equals 1. So where we're headed in this unit, just because we have the 3 x-ints, is making complete sketches of graphs that look like this. So if we have a root at -4, and a root at 1 and a root at 2. And so you can even find something pretty quickly like the y-intercept. Plugging in 0 for the x's would be a y-intercept of like 8, right? The way this graph is going to curve is it's going to go down forever on the left, come up through this root, hit the y-int, come down through this x-intercept, but only for a short moment, because then we have to go back through the last x-int. And see that this last end of the graph is going to head up forever. Okay, so pretty cool stuff here. We're going to have to do a lot more in this unit to uncover ways in which we can find, how should I know what factors I should test to divide into these polynomials? Well, that's going to be something we learn eventually, but hopefully you got a pretty good sense as to what this division process looks like. We will definitely do more practice next time I see you. Have a great rest of your day.